Dear friends, so again I am coming back with this presentation. So in this presentation, basically we shall discuss about the different components of HVDC system, right? So we have already spoken about what is HVDC system, what are HVAC systems, how do you compare the HVAC and HVDC systems, right? What are the advantages of HVDC system over the HVAC system, right? And what are the limitations of your HVDC system over the HVAC system, right? Now, after having taken all those introductory aspects, now let us go into slightly specific aspects of your HVDC system, and we will start with the components. Now, if you look at this particular diagram, which is taken from one of the textbooks, right? So this basically represents a typical HVDC transmission system, right? Now, this is going to be your DC line here. On either side, you have the different components that are associated with the typical HVDC transmission system. Now, let us start with the individual components. First, we will see what are the converters, followed by what are the smoothing reactors on the DC side, then what are the harmonic filters, why do we need the reactive power supplies, where are those in this diagram, then what are the different electrodes, DC lines, and also the AC circuit breakers, right? Please have a careful observation of the diagram before we proceed with the individual components. We speak about the converters, right? We speak about the converter, then we speak about the DC smoothing reactors, then we speak about the harmonic filters, right? So this could be in the form of a DC filter as well as the AC filter, right? Then we have got the reactive power supplies, which is a component of the DC filter also, right? We have got the electrodes here, right? We have got the DC lines here, then we have got the AC circuit breakers, right? So basically the circuit breakers are deployed on the AC side, right? The same thing you can see on the other side also, because as I mentioned earlier, the whole system is symmetric about this particular midpoint on either side. Okay, so now after having a clear and careful observation of this particular diagram, right, we will now go into the details of the individual systems. Let us start with the converter. And in this particular diagram, right, I have taken only a part of the previous diagram, which we generally refer to the individual components of this HVDC system, right? So when I speak about the converter, right, we have already seen what is the converter. This converter could either act as a rectifier or it can also act as the inverter, depending upon the direction of the power flow, right? So if the direction is this way or this way, that will decide each converter acts as a rectifier or the inverter, right? And the explanation is quite simple and it is general, right? Unless we go into the specific details of the converter and all. So these converters perform AC to DC and DC to AC conversion, right? And basically they consist of, now if you look at the converter, this is what is the typical representation of the converter. They consist of the wall bridges and the transformers, and this wall bridges, they depend upon the very requirement of the system there, right? So you may have a 6 pulse or 12 pulse arrangement depending upon the requirement. So you have the voltage and current rating of the SCRs selected in such a way that it may sometimes necessitate the series or the parallel connection of the valves in order to meet the required rating of the the power, right? Power to be carried in the transmission line. So all those things will go with the individual design of the converter system, whether it has to act as a rectifier or whether it has to act as the inverter. All those things will be decided by the actual requirement of the system. And apart from that, you may have a very sophisticated auxiliary systems also here. So gate control logic, right? Or whenever you have got the parallel or series combination of the SCRs, right? So how exactly all the devices are required to be triggered simultaneously, right? How it is achieved. Then the cooling systems, then the snubber circuits, the temperature measurement, so many measuring components, all those things will become a part of this converter system. So that all completely decides how exactly your converter system should look like. Okay, then here the transformers are the devices which provide the input to the converter as long as it is acting as a rectifier, or it will take the output of an inverter if the converter is acting as a inverter, right? So the transformers are generally ungrounded such that the DC system will be able to establish its own reference ground as long as it is connected to the DC side. So this is the basic structure how a converter system looks like in your HVDC system. Now, with that little explanation about the converters, let us move on to the next aspects. Now, the next thing is that the smoothing reactors. So these smoothing reactors also, in one or the other way, we have come across in our previous presentations, right? So this smoothing reactor, they are the high reactors with the inductance value as high as 1 Henry, right? In series with each pole. This is in series with each pole, and the very function of the smoothing reactors is to decrease the harmonics in the voltage and currents in the DC line, right? So this is one thing, right? Apart from that, it is also used to prevent the commutation failures in the inverters, the smoothing reactors, and it is also required to prevent the current from being discontinuous, right? Being discontinuous whenever you have the light load conditions. In the basic power electronic circuits, you must have come across all these issues, right? How do you make the current continuous by having the inductor? The energy is stored there and it is released whenever the reverse cycle start. All those things you have studied, and these are the basic three purpose of why the smoothing reactors are used. They are basically used to decrease the harmonics in the voltages and currents in the DC line. They are also used to prevent the commutation failures in the inverter, and they are also used to prevent the current from being discontinuous, especially when the system is operating with the light load. So these are the three major applications of the smoothing reactors. The design and all that depends upon what exactly is the system requirement in terms of the voltage rating, in terms of the current rating, in terms of the power rating, and also in terms of what is the maximum load that is put on the transmission line. Okay, now after having seen the smoothing reactors, now the next aspect which we have to see here in this particular case is about the harmonic filters, right? So now the harmonic filter, whenever I speak about the harmonic filter, you can see here there are certain filters. AC side also there are certain filters. Now what I mean by the harmonic filters is that they are basically used to mitigate the harmonics, right? Harmonics are the uh, components of the undesired frequency signal. They are basically formed due to the rapid formation and collapse of the magnetic field, right? So harmonics are generally the undesired frequency components which unnecessarily generate the heat and other things. We have already studied about these harmonics, right? So the converters, as usual, they generate the harmonics both in the form of the voltage harmonics as well as the current harmonics, and these cause overheating, right? And the nearby generators or the telecommunication systems, they all get affected by the very generation of the harmonics. In order to prevent these harmonics or the filter out these harmonics, right, the harmonic filters are deployed in your the HVDC system, right? Now Next is about the reactive power supplies. We have seen already, right? So when we speak about the reactive power requirement up to here, right, up to a certain distance, you have the reactive power required for the. This is one drawback which we have taken in case of the HVDC system, right? So the reactive power is essential as long as the converters are concerned, not in the transmission system. Again, I will get this point reminded, right? So under steady state condition, the reactive power consumed by the converter is about 50% of the active power transferred, right? So see here, so this is one important point which is to be kept in mind, which increases the overall losses as well as the cost of your HVDC system in comparison with the AC system. In the steady state condition, we say that about 50% of the total active powers capacity is converted, is consumed as the reactive power in the converters, right? And under transient condition, it could be much higher than, it can go up to 70% or 75%, right? So therefore, the reactive power, it is provided near the converters, right? So because your lines should not get occupied with the reactive power, and nevertheless it is a DC line, so the reactive powers are supplied near to the converters, right? So we have also seen in our facts discussion that you have to avoid the transmission line unnecessarily getting engaged with the reactive power. So as and where the reactive power is required, there only you have to make the arrangement to supply it or swallow it. So that is the reason why the reactive power sources are generally deployed near to the converters, right? So for AC power system which are very strong, these reactive powers are generally provided by the shunt capacitors. This is a general thing which we have already discussed in our facts discussions, right? So the reactive power supplies, why the reactive power supply is required, right? And how exactly the reactive power supply is given to the converters, that we have seen in this particular slide, right? Then after that, we have certain general things, right? One is with respect to the electrodes. These are the conductors that provide connection to the earth for the neutral purpose. They have surface to minimize the current densities and surface voltage gradients, right? So what the electrodes here, we've already seen in our monopolar, right? Then bipolar, then our homopolar DC links, right? What are the roles of the electrodes that we have to that they have to play, that we have already seen. Then the next things are very, that is the DC line. These DC lines could be the overhead lines, or they could be the cables, right? So they are very similar to AC line. Nothing much to explain about the DC lines here, right? And the AC breakers. So the AC circuit breakers are basically used to clear the faults in the transformer for taking the DC link out of the service, right? So they are not used for the clearance of the DC fault, because AC circuit breakers cannot be deployed, right, for clearing the DC faults. You need to have the DC circuit breakers. That is one of the major bottlenecks or the limitations as long as the HVDC system is concerned. Nevertheless, right, so in order to clear the DC faults, generally the converter control itself is used, because you have got a very sophisticated, very quick acting, very fast acting, very accurate and very reliable converter topologies. So whenever there is a fault in the DC line, definitely the converter itself, or the control of the converter itself, can take care of clearing these faults based on their operations or based on their modes of operations. Okay, so now these are certain components as long as the HVDC system is concerned. Now within that, as a part of that, we shall look into one more important parameter, which is referred to as back-to-back HVDC converter, right? So this back-to-back HVDC converter is a special type of HVDC converter which generally doesn't fall into the category of whatever we have discussed so far, but it is basically to interconnect the two systems with two different frequencies, right? F1 and F2. Let us take an example of the Brazil and Argentina, right? So you know that Argentina and Brazil are the two neighboring countries. One of those countries works with the frequency of 50 hertz, the other works with the frequency of 60 hertz, right? You know that the two systems with two different frequencies cannot be synchronized because of the stability and other issues. So now whenever you want to have the synchronization of these two, or whenever you want to have the connection of these two, then this is achieved with the help of the back-to-back HVDC links, right? And it is also to connect a weak grid, right? What we mean by weak grid is generally the rural grids and all, which are very much sensitive even for the small faults and all. The entire grid may get collapsed and all. So in order to connect the weak grid, to stabilize the weak grids, the back-to-back HVDC converters are used, right? So now it will, again, you can go through these points. With a back-to-back HVDC configuration, two independent neighboring system with different and incompatible so these electrical parameters could be either in the form of the frequency, or it could be in the form of the voltage level, or it be in the form of the short circuit power level. They are connected via the rectifier and inverter are located in the same station. Please compare it with your actual HVDC system. So your rectifier is here. You may have hundreds of or thousands of kilometers of your transmission line. Then you have got the inverter on the other side. But here in your HVDC converters, which are back-to-back in nature, both the rectifier as well as the inverter are located on the in the same station, right? Because the very purpose of this back stations is not for the long distance power transmission, DC power transmission, but they serve some different purpose of having the asynchronous high voltage power system with two different frequencies connected, and also to stabilize the weak or a sensitive AC links, right? So basically the HVDC converters with the back-to-back topology, they are used to connect asynchronous high voltage systems or systems with different frequencies, and also to stabilize the weak grids, right? To supply active power where the AC system is already at its limits on the short circuit capability. It is already supplying the power up to its short circuit capacity. So if you want more active power to be supplied, then the back-to-back converters are used, right? And also the grid power flow control within the synchronous AC system, right? So now in order to have the control of the grid power flow within the synchronous AC system. So these are the 4 points which you should keep in mind as long as your HVDC transmission system is the back-to-back HVDC converters to connect a synchronous high voltage power system with different frequencies, to stabilize weak AC grids, to supply more active power when the system has already gone into its short circuit capability, and for the grid power flow control within the synchronous AC systems, right? So now let us try to see how exactly this back-to-back system looks like. You can see here it is very similar to what we have seen in our earlier system, but only thing is that everything will be located in a single yard, right? So you have the AC switch yard, then AC filters here, the number 2, the transformers here, then again the converters or valves, the valve hall, because it's a big system. Then comes your actual part of the scheme here, this one, the 5th one, right? And in our conventional HVDC system, it has got a long distance, but here it is located in the same yard, right? So then again you have got one, second one, and first one, because with respect to this particular point, this diagram is symmetric. So now this system, whatever we have represented here, it is in a single yard, same switch yard. We have got one HVDC back-to-back system in Chandrapur, Maharashtra, and so many others also. And when I take up the different case studies in our subsequent slides, I will tell you what are the different types of the HVDC systems in India as well as across the globe we have. Okay, with that I will stop this presentation, and in our next presentation I will come up with the certain case studies related to the HVDC system.